Welcome to this explainer. We're diving straight into these intricate, handwritten physics notes to build a real, ground-up understanding of classical electromagnetism. Our main focus today? The functional link connections between microscopic electron drift and complex multi-loop circuit logic. We're going to rely heavily on reasoning-based mechanics to see exactly how these fundamental rules govern literally every device we use today. Here is our roadmap. We'll start with the foundations of electric current, then move into resistance, power, and energy. After that, we'll tackle grouping cells and EMF, followed by Kirchhoff's circuit laws. Finally, we'll wrap the whole thing up with the Wheatstone bridge principle. Let's get right into it. Section 1. Foundations of electric current. At its core, current is simply the flow of charge over time. But here's a really fun detail. Even though current clearly has a definitive direction when we map out our networks, it's actually a scalar quantity. Why? Because it strictly follows the rules of basic algebra, rather than vector addition. Now let's derive Ohm's law, step by reasoning-based step. We start with drift velocity, which is just the average speed electrons actually travel through a conductor. By substituting that drift velocity into our current equation and then functionally linking the electric field to voltage, we can mathematically prove that the ratio of voltage to current is a constant. Think about that massive cluster of variables: mass, length, number density, electron charge, relaxation time, and area. They all elegantly combine to define what we casually just call resistance. Section 2. Resistance, power, and energy. Notice how material behaviors can be so fundamentally different. Ohmic elements, like your standard metals, strictly obey linear voltage-current scaling. That's why they map out as a perfect straight-line slope. But non-ohmic materials, like semiconductor diodes, they behave entirely differently. The relationship actually curves, which tells us mathematically that resistance isn't just a flat constant, it fundamentally changes based on the applied voltage. So what happens when electrons face that resistance? Well, it essentially converts that flowing energy into power. Electrical energy is the total work done by a source just to keep the current flowing. Power, on the other hand, is simply the rate at which that energy is being consumed. We measure this power in watts, or if you're looking at really practical engineering applications, horsepower, where 1 unit equals exactly 746 watts. Section 3. Grouping cells and EMF. To really understand real-world power sources, we have to reason through the difference between ideal output and actual output. A cell's ideal EMF, for electromotive force, is its absolute maximum potential in an open circuit. But the actual terminal potential difference you get when that circuit is closed, it's always less, because the cell itself is a physical object. It has its own internal resistance that drains a fraction of the energy before it even leaves the battery. It's kind of like a built-in tax. This inherent limitation gives us a massive, practical engineering challenge. Think about it. If a single cell is constantly held back by its own internal resistance, how exactly do we group multiple cells together to truly maximize our current output? Well, one option is a series combination, where we functionally link the cells end to end. This is great because it multiplies the total EMF. But because there's only one path for the current, we also end up stacking all their internal resistances together. So your total resistance becomes the external circuit's resistance plus the sum of all those internal cell resistances. Alternatively, we can arrange those cells side by side in parallel. Now, doing this means the total EMF stays exactly equal to just a single cell. But here is the massive advantage. This arrangement drastically reduces the total internal resistance of the entire power system. So, to summarize the reasoning here into a quick cheat sheet, the right choice depends entirely on your specific hardware. You want to go with a series setup when your external resistance is huge compared to the cells. Conversely, use a parallel setup when your cells have a really high internal resistance. And for mixed groupings, current hits its absolute maximum when the external resistance perfectly matches the total internal resistance of the grid. Section 4. Kirchhoff's circuit laws. Okay, so what happens when our circuit has multiple power sources and branching loops that basic Ohm's law just can't calculate? We rely on Kirchhoff's laws. And these are definitely not just arbitrary rules. They are direct, practical applications of two fundamental universal truths. Kirchhoff's first law, the junction rule, is literally just the conservation of charge. And Kirchhoff's second law, the loop rule, is the strict conservation of energy.
Now, applying Kirchhoff's second law to navigate closed loops is incredibly cool. By using strict sign conventions, we can traverse complex networks to solve for completely unknown currents. When we travel in the exact direction of the current across a resistor, we mark that potential difference as negative. And if we hit a battery's negative terminal first, we take the EMF as positive. Carefully, and I mean very carefully, tracking this around any closed loop ensures the sum of all voltages definitively equals zero, every single time.
Section 5. The Wheatstone Bridge Principle.
Let's apply these conservation laws to a classic engineering challenge. The Wheatstone Bridge is an ingenious arrangement consisting of 4 resistors. 3 are known, P, Q, and R, and 1 is unknown, S. Sitting right in the center, functionally bridging the 2 parallel branches, is a galvanometer. That's a highly sensitive device used to detect even the absolute slightest trickle of current.
And here is where the reasoning-based magic really happens. We tweak the known variable resistor until the entire bridge is perfectly balanced, meaning the galvanometer registers absolutely zero current flowing through that center bridge. Because no current is flowing across it, we know for a fact that the electrical potential at both ends must be strictly equal. By applying Kirchhoff's loop law to the top and bottom triangles, we mathematically prove that the ratio of the arms has to be equal. P over Q equals R over S. With 3 knowns and 1 beautifully simple equation, we can flawlessly calculate that unknown resistance.
As we wrap up this explainer, I really want you to step back and think about the sheer scale of what we've just decoded. Consider how these elegant, functional links between charge, energy, and resistance don't just exist as ink on handwritten notes. They are the absolute, literal blueprint for every piece of modern technology we rely on. From the microflow of drift velocity to the incredibly complex loops of the global power grid, these mechanics are everywhere. So the next time you plug in your smartphone, ask yourself, which microscopic interactions are quietly balancing the loops of your life? Thanks for exploring this with me, and keep questioning the mechanics of the world around you.